Hello everyone, welcome back to Mind and Maths with Amna. Today we're beginning our topic on difference equations. To keep the learning experience calm and focused, I'll be keeping each video under 30 minutes. So this topic will be covered through a small series of short lessons. In this first part, we'll start with first order difference equations, then second order difference equations, coupled systems, and later we'll look at how these are used in economics. Difference equations are essential for understanding how variables evolve over time, especially in discrete time models. So let's begin slowly and build intuition step by step. So, beginning with first order difference equations, let's set up a very basic system. Yt minus beta yt minus 1 is equals to g, where g is a time independent constant. We know that the general solution of this system consists firstly of a homogeneous solution and then a particular solution. So let's start by first finding the particular solution. For the particular solution, since our constant g is independent of time, therefore my guess for the particular solution is going to be a constant y bar. Putting this in the equation, I get a y bar minus beta y is equals to a g. When I take y bar as common, I'm left with what minus b. I'm going to make this the subject, and I'm left with g over 1 minus b. For this to be defined, I have to make sure that beta is not equals to a 1. So therefore, our particular solution is a g over a 1 minus beta, where beta is not equals to a 1. What if beta is equals to a 1? Let's discuss that for, we can just add a side note. What if beta is equals to 1? What happens then? So if beta is equals to 1, we take our trial solution for the particular equation to be dependent on time. So what does this mean for our equation? Yt minus beta yt minus 1 is equals to g becomes ty bar minus beta into t minus 1 y bar is equals to a g, and therefore y bar is equals to g over 1 minus t minus it is a t minus beta t minus 1. So in this scenario, the particular solution will be a g over t minus beta t plus a b. So this is the scenario when we have a denominator which becomes a 0, giving us an undefined quotient. However, we're going to stick with this one, so we're going to assume that in our scenario beta is actually not equals to a 1. Okay, moving on to the homogeneous solution of the system. Homogeneous, I don't know how we should pronounce it. I think both is fine. Okay, so this is the solution to the system when the constant is equals to 0, or whatever. It's basically this solution of this system. yt minus beta yt minus 1 is equals to a 0. So the solution to this system is called the homogeneous solution. So how do we find it? What should our trial solution be? First, we're going to state our trial solution, which in this case is going to be a constant a lambda power t, where I'm going to say a is a non-zero constant. Once I plug this, I'm going to plug this into this equation. So we have a lambda t minus beta lambda t minus 1 is equals to a 0. Oh, there was an a as well here. We can take a lambda t as common and we're left with 1 minus beta lambda power minus 1 is equals to 0. Since a and lambda are not equals to 0, therefore 1 minus beta lambda power minus 1 should be equals to 0. Therefore 1 is equals to a beta over a lambda, and lambda therefore is equals to a beta. Hence our homogeneous solution equals a beta power t. So we're all very close to the end. So our general solution, like I said before, the general solution is, which is basically the final solution, that is the homogeneous plus the particular. Therefore, I'm going to write it out as the homogeneous plus the particular, where we know one condition being imposed, that beta is not equals to a 1. Now over here we have this one unknown constant. So we should impose a initial condition. So let's see what happens at time t is equals to 0. The reason I am taking t power 0 is because I know any constant power 0 is going to give me a 1. So when I plug this in, I'm going to get a y naught is equals to a plus g 1 minus beta, and therefore I needed the value of the unknown constant a, so that's going to be y naught minus g over 1 minus beta. Hence now we can write our final solution. So our final solution, the final answer is therefore a yt is equals to y naught minus g 1 minus beta into beta power t plus g 1 minus beta, where beta was not equals to a 1. So for this model to be stable, we need this series to be convergent in the long run. By that I mean, if I take the limit of yt as t approaches infinity, I need a finite plus unique value constant as my answer. The only way I'll be able to do that is if the limit of beta power t as t approaches infinity will be 0. And this is only possible when beta in fact is a constant. That is, beta lies between a 1 and minus 1. So if beta lies between 1 and minus 1, we're going to have a long run stable level of income, which is going to be g over which is going to be y naught minus g over 1 minus beta this becomes a 0 plus g over 1 minus beta. So our particular solution becomes the long run output. One thing to be careful about is that when we state the stability condition, we write the stability condition as the absolute value of beta being less than 1. However, we should know that when the value of beta is a fraction, which is a positive fraction, then we know that the output or whatever equation we are going to have a smooth convergence. If the value of beta is a fraction which is negative, so if the value lies between -1 and 0, then we have this kind of oscillatory kind of convergence. And if the value of beta, let's suppose, exceeds 1, we know this is unstable model. However, we can say this in this scenario it explodes. So it's unstable and it explodes. And the last option, if beta is less than -1, then we say it is exploding, but in a oscillatory fashion. So it's oscillatory, it's rising in a oscillatory fashion. It's still unstable. Okay, so this brings about an end to first order difference equations. In order to begin the second part, which is trying to solve and also understand second order difference equations, we need some preliminary knowledge about what complex numbers are. So before I begin second order difference equations, I'm just going to give a small recap of the knowledge that we need in order to solve these. So I'm just going to call this the preliminary knowledge required to understand the second order difference equations. Okay, so suppose we have a complex number. All of us know what a complex number is. A complex number has a real part and imaginary part. So it has a real part and it has an imaginary part. So what I can say is the real part is A and the imaginary part is simply B. To give myself a good visualization of this, what I can do is I can just make a plane. I can say that this is the real part of the complex number and this is the imaginary part of the vertical axis is the imaginary part. And we make a point here and we say the real part is A, so I label that as A, and the imaginary part is B. Okay, let's suppose the length of this vector is R, and let's suppose this is a 90-degree angle and this is an angle of theta degrees. So by the Pythagoras theorem, we know one thing. If this is opposite the angle, this is B, this is adjacent, which is we can see of length A. So by the Pythagoras theorem, R square is going to be equals to A square plus B square. And according to the sine of theta is going to be opposite over adjacent. I think it's hypotenuse actually. Yeah, I think it's hypotenuse. So it's going to be over R. and cos of theta is going to be adjacent over hypotenuse. Therefore, we have b is equals to sine theta and r sine theta, and a is equals to r cos theta. Okay, so we are going to put these in the above equation. So we had we had z, which is a complex number which equals a plus ib. We found a as being r cos theta, and we found b as being r sine theta. If we take r out as common, we're left with cos theta plus I sine theta. So basically, we've just figured out two ways of representing a complex number. So the first way is, so a complex number can be written as a plus ib, or it can be written as r cos theta plus I sine theta. However, there is also a third way to represent it, which is r e I theta. Let's prove this point. According to the Maclaurin series, which is basically a Taylor series around a point x is equals to 0 or a is equals to 0, we have as follows: the expansion of the Taylor expansion of ex around 0 is ex is equals to 1 plus x square over 2 factorial plus x3 over 3 factorial, and so on. While the Maclaurin series of sine x, which is the Taylor series of sine x around 0, is x minus x3 over 3 factorial plus x5 over a 5 factorial. And lastly, the Maclaurin series, which is the Taylor series of cos x around point 0, is 1 minus x square over 2 factorial plus x4 over a 4 factorial, and this basically continues, and this also continues. Okay, so looking at ex, I'm looking over here. If I take x as I theta, knowing that iota is basically the imaginary number whose value we know is I square is equals to a minus 1, and therefore an I is usually written as under root of minus 1. So knowing this, let's find the value of ei theta. This is going to be, I'm just substituting it in the equation. It's a 1 plus I theta over a 2 factorial, but we have a square here, plus I theta cube over 3 factorial plus, let's just do one more till the 4th order, over 4 factorial, and then we can just say and so on. This continues. Okay, opening this up, we get 1 plus I theta minus theta square over a 2 factorial. Why so? Because I know iota square is a minus 1. Okay, going ahead, then we have a minus iota I theta 3 over 3 factorial. Then this just stays like this, 4 factorial. what I'm going to do is I'm going to keep these terms together. One, all the with the power even powers I'm going to keep together, and all the odd powers I'm going to keep together. So what does this become? I'll just make a big bracket, 1 minus theta square over 2 factorial plus theta 4 over 4 factorial, and so on. After this, I'll take the imaginary I out as common, and I'll be left with theta minus theta cube over a theta factorial, and we can guess that this is going to be a theta 5 over a 5 factorial, and so on. So I'm just going to make a dotted line here and then close the bracket. Okay, so what is this? This is basically the Maclaurin series for cos x. And what is this? This is the sine x series. So we can replace this. We can say that this is the Maclaurin series for cos theta, and that is the Maclaurin series for sine theta. Hence, we've figured out that cos theta plus I sine theta is also equals to ei theta. So as a recap, we know that an imaginary number which is a plus ib can be written as r cos theta plus I sine theta, and we've just seen that cos theta plus I sine theta can be written as r as ei theta. Another preliminary knowledge that we need to know is the I have no idea how to pronounce this. De Moivre, I guess. Maybe it's a French word. I don't know. De Moivre. I'm going to search this up later. So the formula says that cos theta plus I sine theta power n is equals to cos n theta plus I sine n theta. And this can be proved using induction, and that's a lecture for another day. So for now, we're just going to state this formula without proving it. Okay, now we are in a place where we can start solving the second order difference equations. I'm just going to write a generic format in which these usually appear, and I'm going to take an easy generic example. So yt plus beta yt minus 1 plus beta 2 yt minus 2 is equals to g. Since g is independent of time, therefore for the particular solution we can assume that it is independent of time, and therefore it is a constant equals to y bar. So once I put this trial solution into my main equation, I get a y bar plus beta 1 y bar plus beta 2 y bar is equals to a g. And when I take y as common, I'll be left with 1 plus beta 1 plus beta 2, and since the quotient will be undefined if the denominator is 0, so therefore we are going to have a beta 1 plus beta 2 not equals to minus 1. or yeah, because it can't equals to it cannot be equal, the denominator cannot be equals to a 0. Okay, what happens if beta 1 plus beta 2 is equals to a minus 1? Then what we can do is that we can say the particular solution is dependent on time, and once we place that in the main equation, we'll get something like this. We'll get ty bar plus beta 1 t minus 1 y bar plus beta 2 t minus 2 y bar is equals to g, and therefore the particular solution will be a g over a t plus beta 1 t minus 1 plus beta 2 t minus 2. So this is just for the case where we end up with a denominator which is actually equals to 0, and we can't have that. Okay, coming back to the homogeneous solution, continuing on to so the homogeneous solution is the solution of the system when this equals to 0. So the solution to this system is known as the homogeneous solution. So what is our trial solution going to be? Same as before. The trial solution is going to be yt is equal to some constant a and alpha power lambda power t. I don't know why I keep saying alpha, it's actually a lambda. Alpha is this is an alpha, this is actually a lambda. Okay, so we get a lambda t plus b1 a lambda t minus 1 plus beta 2 a lambda t minus 2 is equals to 0. If I take a lambda t out as common, I'll be left with 1 plus beta 1 lambda minus 1 plus beta 2 lambda minus 2, and this is going to be equals to a 0. Since a and lambda are not equals to 0, therefore 1 plus beta 1 over a lambda plus a beta 2 over a lambda 2, this is going to be equals to a 0. So we have lambda square plus beta 1 lambda plus a beta 2 is equals to 0. Okay, at this point, this is a quadratic equation, right? So we can find the solution by using that formula, x is equals to minus b plus minus b square minus 4ac over 2a. So let's do that. So it's going to be a minus beta 1 plus minus beta 1 square minus 4. The value of a is 1 and c is beta 2, and over 2 into 1a. Okay, so now we have three possibilities. So we have a case where when we get two roots, lambda 1 and lambda 2, which are real roots such that they are distinct. So lambda 1 is not equals to lambda 2. So we get two roots and they're distinct. So we have real and distinct roots. Okay, so then the solution, the homogeneous solution to such a system is going to be some constant c lambda 1 power t plus some constant d lambda 2 power t. And therefore, the general solution will become, so the general solution in such a scenario will become the homogeneous, which we can write like this, plus the particular. So this is going to be the general solution with C and D being two unknown constants. So C and D are two unknown constants. So in order to find these constants, we'll need two equations, because if you want, we don't want infinitely many solutions. So for that we need, when you have two unknowns, then you need two equations. So therefore the first equation will be at time t naught, and we're going to get a C plus D, and this remains the same. And then at time 1 we have a C lambda plus D lambda plus G 1 plus beta 1 plus beta 2, and therefore we can solve this simultaneously to find the value of C and D. Another way of doing is instead of solving it simultaneously, we can just convert it into matrix form. So in matrix form, this is going to be as follows. The unknown constant is CD. We have a 1 1 here, and we have a lambda 1 lambda 2 here, and over there we have a y naught minus G over 1 plus beta 1 plus beta 2, and over here we have y1 minus G over 1 plus beta 1 plus beta 2. You can solve this using either row operations or taking the inverse or using the Cramer's rule. But basically you can solve this to find C and D. Okay, moving on. So we've covered case 1. There's another possibility, which we can say case 2, which is that we have roots that are real but are not distinct. So we have real but same roots. In this scenario, our homogeneous solution is going to be Ct plus D into lambda power t, because both our roots are the same. I'm just taking that, though both of them is equals to lambda. So therefore our general solution is going to be Ct plus D lambda power t plus the particular, which is a G over 1 plus beta 1 plus beta 2. So this again is our general solution, which has two unknown constants, just like before. This also had two unknown constants, and we solved it by putting in two conditions, because we needed two equations. Similarly, again for this, you will just put in this, we'll solve this for t is equals to 0 and t is equals to 1. You'll obtain two equations, and then you just need to solve them simultaneously. When you solve them simultaneously, you will obtain the answer to the unknown constants. So these will become known. Okay, the last scenario before we end the class is the final case 3, where we get complex roots. So sort of like the worst case scenario when it comes to second order difference equations. So what was the value of lambda? This was the value of lambda. The only way this is going to become a complex root is if this expression is less than a 0. So what I'm going to do is I'll just write it like this: minus beta 1 plus minus a minus 1 multiplied by 4 beta 2 minus beta 1 square. Okay, so since these two are being multiplied, what I can do is I can just write them separately. So I can put an under root on this one separately, and I can put an under root over here separately for this. Oh, this wasn't a whole square, it was beta 1 square. Beta 1 square, my bad. Okay, we know that I square is a minus 1. Therefore, I is going to be the under root of a minus 1. So we can basically write this whole thing as I under root of 4 beta 2 minus beta 1 square over a 2. Okay, so there is, as you can see now, there's a real part of the solution, and then we have an imaginary part of the solution. So this is the imaginary part. For ease of notation, let's say that lambda is u plus minus iv. So just for ease of notation, I'm taking u and v to denote these constants. So what does this mean? My first root is basically a u plus iv, and my second root is a u minus iv. Okay, so what will the homogeneous solution look like? We know the homogeneous solution should be some constant c lambda 1 power t plus constant d lambda 2 power t. So for lambda we have a u plus iv power t, and for d for lambda 2 we have u minus iv power t. As you know, we represented this using cos and sine. So I can write this as r cos theta plus I sine theta, and power t. Let's go ahead with the next one. I can write this constant, this complex number as using cos and sine as well. It's going to be an r square, and I'm going to be left with cos theta minus I sine theta power t. Okay, so now I'm going to use that de Moivre law, in which the power can basically go inside. So if I take RT out as common, I'm going to be left with C cos t theta plus I sine t theta, and then I'm going to have a D, and I'll have a cos t theta minus sine t theta. Okay, now I can see that, oh, there was an I here as well. I can see that I can take this together and I can write this together. So let's move on with the taking it as common. If I take cos t as t theta as common, I'll get a c plus d into cos t theta. And if I take sine t theta out as common, I'll be left with a c minus d sine t theta. And therefore, I can say that these are some numbers. I can say this is e cos t theta plus f sine t theta. So basically, the solution, the overall final solution will become r t and this plus the particular solution. Now we have the general solution. Again, we have two unknown constants. So therefore, the same trick applies, that if you put time t is equals to 0 and t is equals to 1, you'll get two equations. You solve them simultaneously, and therefore then in this case you will get the answer for E and F, and therefore they will become known. This brings an end to our discussion. I will make a part 2 of this video in which I will continue this lecture, and I will discuss how we solve difference equations which are coupled, and also some applications. So that's going to be in the next lecture. I hope you guys enjoyed this video and learned something, and hopefully see you next time.